Hello everyone, and welcome to your pre-calculus notes for the week of March 30th. This is section 2.2, polynomial functions. My name is Mr. Gallagher, and I'm going to put together two videos here for this week for the polynomial functions section. And before we get started, there is some pre-printed follow-along notes that you can get in eCampus. So if you want to go ahead and get those first and maybe print them out if you can. If not, you can just follow along with the video. But go ahead and pause here for a moment and you can go ahead and grab those from eCampus, and we'll be back ready to begin in a moment. Okay, so here we go. Again, this is part one video, and we'll have both of these videos that go along with the assignment for section 2.2 polynomial functions. So I want to start off by talking about types of graphs that we already discussed last quarter. We talked about the f of x equals x squared graph, which is a parabola, and then also the f of x equals x cubed graph, which is kind of like a flattened out S-shaped graph. And here's some other graphs that are very similar as well. And I want to talk about first, you'll notice the first example I have is f of x equals x minus 3 quantity to the 5th power. And this is an odd degree function, as it says here. An odd degree, so meaning that the exponent outside is going to be an odd number. In this case, it's 5. And because it's an odd degree function, all of our basic odd degree functions kind of look like x to the 3rd, meaning that it starts going down and then it comes a little bit of a curvature and then it goes up to the right-hand side. So all of our odd degree functions will do that. Whether it's to the 5th or 7th or 9th is just going to make it a little bit flatter, wider. But for sketching, that's not really important. What is important in this example is that we have the minus 3 inside. And what does the minus 3 do to this graph? Well, it shifts it over to the right. So we notice that instead of going through the point 0, 0, it's going to go through the point 3, 0 right now. So the graph moves to the right. And so it's basically the x to the 5th graph, which is translated 3 units to the right. The second graph we have, and you have a copy of this on your notes as well, is x to the 6th minus 1. Well, because this is an even degree function, this is going to be a graph that looks very similar to y of x squared, or y equals x squared. So this is going to be a graph that kind of looks like a parabola, and it points upward on both ends. Both ends go up into infinity as we draw this graph. Now, what does the minus 1 do here? Because it's outside the parentheses or outside the function, it actually moves this graph down 1 unit. Again, so the vertex, instead of being at 0, 0, it's going to be at 0, negative 1. So those are basic functions that we have with and movements of some of the graphs based on the exponent or the degree that we have, whether they're odd or even. This is going to lead us into what we're going to talk about or focus on a lot in this section is the end behavior. And the end behavior is what's happening as this graph continues to infinity. We just saw in that previous example where the graph could go down one direction, up in the other direction, or maybe both up, and we can even see them go both down as well. And we're going to determine what these graphs are going to do by what's called the leading term test. So let's say I'm going to give you an example. Let's say I've got a function f of x is equal to let's use 3x to the 6th plus 7x to the 4th minus 2x plus 3. Here's an example of a polynomial. Now, because of all these different terms and exponents, we want to talk about what's happening at the end of these graphs, the end behavior, as the arrows continue out towards infinity. So what we're going to do is we are going to look at this term right here, this 3x to the 6th power. And based on the characteristics of that, we can determine what this graph does. So first of all, two terms I want to bring up here. The degree of this particular term is 6 because that's my exponent, and the leading coefficient is 3. So the number in front of the variable is 3, and the degree or the exponent is going to be 6. So based on those two things, we are going to determine what the end behavior is of these graphs. And we're also, and you can see this little chart that we have here. And also we're going to use something called limit notation that we have, that I've noted over here on the side. And limit notation is going to be a way of writing or describing what that end behavior is. So for instance, we're going to look at the limit as x approaches infinity. So meaning what's going to happen as x gets closer and closer to infinity as it goes off in one direction. The limit of that function f of x as x approaches infinity, we're going to use this little arrow notation. What happens? Well, that's what we're going to look at here on the one hand side. And the other part of the graph, we're going to look at, well, what happens to f of x, the limit of f of x as x also approaches negative infinity. What's going to happen there? Now, based on the degree and the leading coefficient, we're going to be able to determine that. So let's look at this chart. This chart's broken up into 4 parts, and I want to talk about the leading coefficient first. If the leading coefficient, which they call a sub n, the leading coefficient, if that is positive, if the leading coefficient is positive, I'm going to break this up into 2 parts here. If the leading coefficient is positive, then what's going to happen is the graph is going to look similar to what we saw on that previous page. If it's an odd graph, it's going to go up and down. And if it's an even graph, if it's an even exponent, it's going to go up and up. So if my degree is odd, I'm going to have one side pointing down, and I'm going to have one side pointing up. If it is an even degree polynomial, then I'm going to have both sides pointing up. And again, this is only when my leading coefficient is positive. Now, what happens when my leading coefficient is negative? Well, when my leading coefficient is negative, I'm going to have just the opposite. We know a negative leading coefficient is going to flip my graph upside down. So in this case, when it's an odd odd degree, I know instead of going down and up, I'm going to go up on the left and down on the right. When it's an even degree and it's a negative leading coefficient, both sides are going to point downward. And this is how we can determine what our end behavior is. Now, we can write this again, as I mentioned, using our limit notation. So in this case, we have a degree of 6, that's even, and a leading coefficient of 3, which is positive. So we're going to look at even and positive, which is this box right here. And we know that our end behavior is going to go up or towards infinity in both directions. So if you'll notice, as it says here on this box, whenever we have an even degree and a positive leading coefficient, the limit of x as it approaches negative infinity is going to be infinity. And the limit as x approaches infinity will also be infinity. So for the problem that I wrote up here, the limit as x approaches infinity is going to be infinity, and the limit as x approaches negative infinity is going to be infinity, meaning both of these arrows are pointing up. So let's look at some examples now using what we just learned. So here I've got another polynomial. I want to describe the end behavior of this particular graph using limits. What's the only term I have to look at here? I've got to look at that 3x to the 4th. So what do we know? My degree is 4, and my leading coefficient is 3. Because my degree is 4, it's even, and my leading coefficient of 3 is positive, then what do I know about my end behavior? Well, the limit as x approaches negative infinity of f of x, that's my left-hand side. We know that, let's see, even and positive, again, that's that lower left-hand box of that chart. They are both going to go up, so this is towards infinity. And the limit as x approaches infinity of f of x is also going to be infinity. You try one. Try this one here. Describe the end behavior of the graph of negative 2x to the 5th minus 1. So again, we only need these. And take a minute here. Hit pause if you need to, and I'll reveal the answer in a minute. But what's the end behavior going to be of this graph? Go ahead and hit pause, and when you're done, go ahead and hit play. Okay, last chance. Here's your answer. The answer is going to be 9. not revealed here. The answer is going to be, what do we have? We have our degree is 5, which is odd, and our leading coefficient is -2, which is negative. So what's going to happen here? Well, let's look. Odd and negative, we go back up to our chart. Odd and negative is this box right here. So the limit as x approaches negative infinity is going to be infinity. And the limit as x approaches infinity is going to be negative infinity. So let's write that out. The limit as x approaches negative infinity of f of x, it's going to go up forever, so that's going to be infinity. But the limit as x approaches infinity is going to be downward, so we're going to say that's negative infinity. And those are my two limits of f of x as x approaches infinity and negative infinity. Great. Let's continue. So that's two things we know about. We know about the end behavior on the left and the end behavior on the right. What else do we want to learn about a polynomial when we're graphing these? Well, we want to know what's happening in the middle. So we're now going to look at our zeros and our turning points. How many zeros, meaning how many times does it cross the x-axis, and how many turning points is it going to have? Well, the rule is basically right here. It says a polynomial of degree n is going to have at most n zeros, meaning it's going to cross the x-axis n times at most, and it's going to have at most n minus 1 turning points. Now we say at most is because it doesn't have to have that many. It will have at most that many, meaning it won't have more than that, but it could very well have less. Here's an example. Here's a function, f of x equals 3x to the 6th, and let's look at the degree. The degree is going to be 6. So in this example, right, we have a degree of 6. So since the degree is 6, we know we're going to have at most 6 zeros and at most 5 turning points. Well, if you look at the graph here, we can see where it has 1, 2, 3 turning points, and it crosses or touches the x-axis 1, 2, 3 times. So that's definitely less than 6 and less than 5. But again, that term at most is important here because that's going to tell us the maximum number of turns or the maximum numbers of zeros that a polynomial function is going to have. Let's look at an example. It'll be a lot easier to solve. So here we want to look at the number of zeros and turning points, possible zeros and turning points that this might have. Well, again, if we look at this first term, x cubed, so the degree is 3. So because the degree is 3, we're going to have at most how many zeros, and we're going to have at most how many turns. That's going to be 3 zeros at most and 2 turns at most. Let's solve this algebraically and see if we can prove that. So we have x to the 3rd plus 5x squared plus 4x is equal to 0. Can I factor this? Well, sure. Let's pull out an x, and I get x squared plus 5x plus 4 is equal to 0, right? And then I'm going to factor a little bit further by saying that this is x plus 4, and this is x plus 1 is equal to 0. So what are my zeros going to be? X could be 0, x could be -4, and x could be -1, right? So that means I have 3 zeros, 0, -4, and -1, which we knew we were going to have at most 3 zeros. If I plug this into the graphing calculator, it's going to look like this. And you can double check it. Here are my zeros. I've got one at 0, I've got one at -4, and I've got one at -1. And we said how many turns? It says at most 2 turns. Well, here's a turn, and here's a turn. Change of direction in my graph. Let's talk about the end behavior here. What's happening? This is going up forever. So we can say that the limit as x approaches infinity of f of x, just by looking at the picture, we can say that's going to be infinity, right? And over here, the limit as x approaches negative infinity of f of x is also going to be negative infinity. And that makes sense, right? Because again, this is a odd degree with a positive leading coefficient, right? So as a result, we know that it's going to be, as x approaches negative infinity, my limit is going to be negative infinity, and as x approaches infinity, my limit is going to be infinity. Well, that's it for part 1 of the video. Feel free to go back and replay some things if you need to get a little more clarification. Or we're going to go ahead, if you feel comfortable in this, go ahead and play the video for part 2 of section 2.2, and then we'll have the assignment that goes along with it, all right? Thank you very much. Talk to you soon.